So the period of a pendulum is quite a famous equation in a way. It's not in comparison to things like E equals mc squared or F equals ma or anything, but it's definitely up there as being a bit of a wonky equation to use at times. So the formula I'm just going to state immediately is T equals 2 pi root L over G, where G is gravitational acceleration, L is the length, and T is obviously the time. Now, one thing I actually have to consider first is the understanding of this thing called the small angle approximation. So this is where radians starts to come in. So I'll do a small little thing on what the small angle approximation is. So it essentially removes trigonometric expressions from formulas to make things slightly easier to handle. So there are multiple proofs of this, but in layman's terms, it says that for angles less than pi on 6 radians, which is about 30 degrees, the sine of that angle is approximately equal to the angle, and the tan of the angle is approximately the angle as well. Now, the reason we can actually use this is because the formula for the period of a pendulum involves two weird quantities. So we have pi being irrational, so they can almost be ever there, but we also have g, which is experimental. So you can get closer and closer values to g, but you won't actually get what an exact value of g is, which is why we use approximations for it. So we can actually use the fact that sine A is approximately A, and not necessarily tan. The one weird one is cos A, which is approximately 1 minus A squared over 2, which is a bit weird, but it's like just for completeness sake, really. So how do we actually prove this formula? So this is one we're actually going to prove. So if we just draw a simple pendulum like this, and we let this be at an angle theta away from the equilibrium position, we're going to have the weight acting downwards, mg, which we can split into components with these being similar triangles, and this restoring force being F, and the length of it being L, which I'll denote in a different color. So L is just the length of the pendulum. It's a bit of a wonky arrow or whatever. For completeness sake, we can complete this triangle, and this is F sine of theta, and this is F cos of theta. So because the pendulum is constantly trying to slow itself down, the force is actually going to cause a deceleration. So we get that the force is ma, which means that because the weight force is trying to slow it down, it'll be minus mg sine theta is ma, which just after the cancellation, the acceleration is minus g sine theta. We can replace a with minus omega squared x, and we can make that positive. Now, for small angles, the distance, so this thing in yellow, the distance actually called x, is approximately equal to L times the sine of theta. So this is for small angles, so we can write, I'll write in a different color actually to notate this. So you could say for small angles theta, x is approximately equal to L sine of theta. And so we could write this as omega squared times L sine theta equals minus g sine theta. Now this is, again, the small angle approximation technically comes in. So we can cancel the sine thetas, and we get that omega is the square root of g divided by L. Now, where this comes in, we know that whoops, shouldn't have written it like that. We know that the time period is 2 pi divided by omega. Now, I'm actually going to write this as omega squared. So we can write that t squared is 4 pi squared divided by omega squared, which is 4 pi squared times L over g, just flipping this, which we can then write just simply as t is 2 pi times the square root of L over g seconds. And that is exactly what we were looking for. Now, remember, obviously, this only works for small initial angle theta 0, or just theta. But other than that, that's the formula proven. QED.